Problems and Simple Harmonic Motion. I advise you to take notes. As a warm-up, let's start with a simple spring of spring constant K equals 8 newtons per meter. And I'm going to hang from it a ½ kilogram mass. M equals 0.5 kilograms. And the question is, how far will the spring stretch from me hanging that mass? How far will it be extended? Using F equals negative kx, you might come to the decision that the force is the weight, so that's W equals mg. The force hanging down is 5 newtons, the weight of the ½ kilogram. And that spring constant being 8, and x we don't know, negative. You can always take the absolute value of both sides of an equation and ignore the negative. Completely ignore it and take the absolute value of both sides. Solving for x, you get 0.625 meters or 62.5 centimeters. 62.5 centimeters. 62.5. Let's test it out. Here we go. And go. Whoops. Whoa. Whoa, that went way past that. Let's see that again. Hook that up. 0. Wow. But if we let it come to rest, what did we forget? What did we do wrong? Well, we neglected that the mass would have some kinetic energy when it got there. That is, it would already be moving. It would fall to 62.5 and through 62.5. It would fall twice as much. The mass falls to 62.5 and then it falls another 62.5. Then it stops and bounces back up and back down. This point right here, the 62.5, when the forces balance, is called equilibrium. The point when the force of gravity is equal to the force of the spring in, again, magnitude, in absolute value. Equilibrium is when the forces balance. The net force is 0, and the object is moving as fast as it will ever move, right there in the balance point in the middle. The bouncing on a spring obeys simple harmonic motion. You should already know the formula for the period of a spring is 2 pi the square root of m over k. In our class, we verified this experimentally. I'm going to draw an axis, position x versus time t in that direction. Notice I'm putting x on the y-axis and time on the x-axis. We're going to plot the position of the spring on the y-axis. Now if you watch the spring bounce, it bounces kind of like a sine curve as time goes by. As I walk back and forth with this spring, you can see the mass tracing out a sine shape as I walk with a constant speed. That is the time in the x direction. Let's plot this. So as time goes by, we'll get this bouncing harmonic sine curve. Now the time it takes to repeat itself is called the period, t. So here's one period right here. That's the first period. That's very nice. This position right here is the maximum x. I'm going to call it x max. And here, that's negative x max. The furthest down it will ever be, and the furthest up it will ever be. Same, 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 same. But this position right here is 0. but we're not going to call it 0 anymore. Well, you can call it 0 if you want, but I'm going to call it equilibrium. This point right here, 0, is called equilibrium. Equilibrium. And x is now the extension of the spring and the displacement from equilibrium. We can describe this as a function of time. X, as a function of time, is some sort of sine of t. Notice I'm leaving space here, which I'm going to fill in later. Let's next graph the velocity. I'm now graphing the velocity as a function of time. Notice I'm using the word velocity and not the speed, which might be interpreted as an absolute value. Let's take a look. What's the spring doing? Well, if we actually were to draw in the spring, here, the spring is at its maximum height, and it's all compressed up. There's the mass bobbing on the spring. And here, the spring is all stretched out, and it's at its minimum height. It's the furthest stretched it'll ever be. When something comes to its maximum height, it stops, and has 0 velocity at that moment. At this moment, it's at its bottomest, and it also stops there. It stops at its lowest moment. What's happening here? If we draw the mass, we can see that it's on its way down, from being up top to down bottom. In fact, you might want to just draw it as a motion blur on its way down. This is the fastest it's ever going to get. Down. The fastest, the most negative the velocity will ever be. Negative v max. This is when it happens. Right here. The fastest it will ever be going down. What about here? Right here, it's on its way up. In fact, it was stopped, now it's going up quickly, and it's going to stop again, at the top. But right here, it's going up, and it's going up fast. The fastest it's ever going to be on its way up. We're starting to get the shape of a curve, and I'm going to fill in the curve now. Do you recognize it? This looks like a cosine. Another stop right here completes a little more than a period. That's the period right there. Of course it is. That's the period of the x. That's the period of the v. Right there. One period done. Here is the very beginning, and at the beginning of our problem, the object is on its way up. This point right here is the maximum the velocity is ever going to be. Positive v max. We can see that if the x was a sine, that the v is going to be a cosine. So the velocity as a function of time is some sort of cosine of t. I'm starting to get the feeling that we can fill in the amplitude right here. The amplitude is how big the motion is. The maximum x is the amplitude, the size of the vibration of the x. So x max is the leading term there. But here, what's Vmax? Right now we're just calling it Vmax. I'll show you how to get Vmax later. For now, Vmax is the leading term. But we don't know what goes here. Is it just t? Do I just leave it as t? Let's find out. Lastly, well, I'm going to extend this a little bit more. There's another point of... See, these graphs are always moving together. Lastly, we're going to graph acceleration. Acceleration is the change in velocity with time, but looking closely, there's another way to figure it out. You may have forgotten that f equals negative kx. If f equals negative kx, then ma is negative kx. If the spring force is the net force acting on an object, in that case, the acceleration is negative k over mx. Negative k over m is a constant, so the acceleration will look like negative x. The acceleration will look like a negative x. So if we take x and just flip it upside down, but I'm going to show you that you could have known that anyways. Let's look at this point right here. Here, the spring is pulling really hard up. The spring is pulling the hardest up it will ever pull. So that would be an up, a maximum up acceleration. That's it, right there. This point is the maximum up acceleration we'll ever have, right there. Here, when it stops again, that's the maximum it's ever going to be pushed down. At these moments, these high moments, it's being pushed down very hard. So those are the maximum down accelerations. Pushes down. And what comes in between these? No acceleration. Right here, in the middle, equilibrium, where there's no x, where there's no force, and thus no acceleration. So at these equilibrium moments, there is no acceleration. What does that give us? A curve. Right here is another equilibrium moment. Hello. And here is another negative max moment, followed by a nothing moment, an equilibrium moment. There's your acceleration, and indeed it does look exactly like a negative x. Let's complete the story. So here we stand with these blank spaces in our functions. For the moment, I'm going to put in a constant symbol, omega. Looks like a W. It's the same for all three because they have the same period. But what is the period? Well, if omega times t is 2 pi, then that is a full cycle of sine using radians. If this is 2 pi radians, then the sine of 2 pi is a full cycle. So omega times t is 2 pi, but not just any t, the period, the full cycle. So it looks like omega is 2 pi over t, or omega is 2 pi over 2 pi root m over k. The 2 pi's cancel, and omega just becomes root k over m when you flip. So that's omega for a spring.